So in this video I'm going to show you how you compute a life table. There's a couple of things I need to tell you first about the different kinds of life tables. There's two different kinds of life table. An unabridged life table, which is calculated for single years of age, and that's the example I'm going to be showing you here. You will also find examples of abridged life tables that are calculated for age groups. But it's a little bit easier to understand an unabridged life table, which is calculated for single years of age. So that's the example that I'm going to be going through. This life table is based on the Office for National Statistics UK male life table for the years 2018 to 2021. However, I don't have access to the full workings of the ONS life table, and I've had to compute my own life table. I don't have access to some of the assumptions that they might have made. So you'll find that the life table that I'm showing you here will look slightly different from the official one that the ONS has published. So please just take this as an example of what a life table looks like and an introduction to the basic ideas of how we compute a life table. You don't need any specific statistical software to compute a life table. You simply use a spreadsheet such as Excel. And what you're looking at here is an Excel spreadsheet with a life table computed into it. Now, I know from teaching the second year that some of you will be familiar with Excel, but some of you will not. Unfortunately, I don't have time to teach you Excel in this particular module. I'm only given 3 hours to teach all that I need to teach for quantitative, and that certainly is not long enough to teach you how to use Excel. So for those of you not familiar with an Excel spreadsheet, it's simply a grid with the columns denoted by letters and the rows denoted by number. And each cell in a spreadsheet has a particular code. So this is cell F2, it's in column F, row 2. And in a spreadsheet you can denote either values, such as we have here, or, and if you look at the ribbon at the top, you can have formula. So you can input your raw data and you can calculate the other columns in the spreadsheet using simple formula. So that's what a spreadsheet does. So in this unabridged life table, which is taken from the ONS Male Life Table 2018 to 21, we have a life table for single years of age, and as you see it starts at age 0 and it finishes at age 100. I just need to explain what all of these different columns are. So the first column is simply the age, and you also see that on this last column here I've given an outline of what the different notations stand for, and you can see that in a life table X always stands for age. I'll become obvious hopefully how that works in a life table in a minute. The second column is the MX column, and M stands for mortality. It's simply the column for the age-specific death rates. So MX, this cell here is going to be M0 so X stands for age. So the first cell here is M0, that's M1, that's M2, that's M3. M0 is simply the age-specific death rate between age 0 and age 1. In other words, that's the infant mortality rate. The second rate here is the age-specific death rate between age 1 and age 2. So these data here are the age-specific death rates calculated for single years of age by the Office of National Statistics from data registration in the UK. The third column is the QX, and this is the probability of dying between age X and age X plus 1. You might think, what's the difference between the age-specific death rate, MX, and the probability of dying, QX? Well, it's simply the difference between a rate and a probability, and the difference is in the denominator. I don't want to confuse you by going into too much detail, so I'll explain it briefly, but don't worry if you don't understand it completely. To calculate a rate, we take the denominator as the mid-year population. To calculate a probability, we take the denominator as everyone who is alive at the beginning of the age group. So when mortality is very low, such as in the early age groups, you see that the actual MX is the same as the QX. There's no difference between the rate and the probability. However, when mortality is slightly higher, you will find that there are differences. So, for example, you can see that there's a difference between the MX and the QX. And in fact, the QX is going to be slightly smaller than the MX. The probability of dying during the first year is slightly smaller than the age-specific death rate. And if we scroll down, you can see that the differences actually start to get much greater as mortality starts to get higher at the older ages. I'm not actually going to show you how you could compute QX from MX because it can be a little bit complex and a little bit quite a lot to get your head around. So just understand that we take the age-specific death rates and we can convert these into probabilities of dying between age X and X plus 1. The next column, the PX column in column D, is the opposite of the QX column. It's the probability of surviving between age X and X plus 1. And this is when I have my first formula. So if you look up here on the ribbon, you can see the formula that's inputted here. And it's simply 1 minus C5. So to calculate that first PX value for age 0, so that's P0, it's simply 1 minus the probability of dying. It's quite simple. You either survive or die during each year. Okay? So PX is simply 1 minus QX. That's hopefully relatively straightforward to understand. So the fourth column is the little LX column. Now this is a specific notation to life tables, and I am going to have to call it little LX to distinguish it from big LX, which I'll be coming to in a minute. Little LX gives the number of survivors to exact age X. And I'm going to start off by talking about L0. This is the number of people who survived. I'm going to have to start off by talking about L1, which is the number of people who survived to exact age 1. And L2 is the number of people who survived to exact age 2. And it's very easy to calculate the number of people who survive to exact age 1. We simply have to take the probability of surviving from age 0 to age 1 and multiply it by the number of people who are alive at the beginning of the life table. So if we look at the formula for P1 here, we can see that that's calculated by multiplying the cell D5, that's P0, by the cell E5, that's L0. So that cell there, which is E6 for the value of L1, is calculated by multiplying P0 by L0. This first value of L0 is called the radix, and that's just a number we impute. And convenience, we always use a value of either 10,000 or 100,000. In this particular example, the radix has been set to 10,000. So what we've done is we've taken our synthetic population of 10,000 people. We've applied the probability of surviving the first year of life, and that gives us the number of people alive at age 1. We then take the probability of surviving the second year of life, and we multiply it by the number of people alive at the beginning of age 1, and that gives us the number of people alive at age 2, etc. We can go all the way round, all the way down the life table to calculate the little LX. The next column in column F is the DX column, and D stands for deaths in the life table. It is the number of deaths between age X and age X plus 1. And in the unabridged life table, it's the number of deaths at each age. So D0 is the number of deaths between age 0 and age 1. And as you can see, there were 42.2 deaths in the first year of life, 2.3 deaths in the second year of life, that's between age 1 and age 2, 1.3 deaths in the third year of life. And we can calculate the DX very simply, this time by multiplying the probability of dying during that year by the number of people alive at the beginning of the year. So that DX is calculated by multiplying C5, the probability of dying during the year, by the number of people alive at the beginning of the year. So we started our life table with 10,000 people. The probability of dying during the year is 0.004224, and if we multiply that by 10,000, we get 42.2 deaths. The probability of dying during the second year of life is much smaller, and if we multiply that by the number of people alive at age 1, we get 2.3 deaths. I'm just going now just to scroll down to the bottom of the life table. When we get to the last age group, which here we've set to 100, you'll notice that the DX, the probability of dying, the number of deaths at age 100 is the same as the number of people alive at age 100. Quite simply, there's no immortality in a life table. Everyone has to die. So in the unabridged life table, the last age group, the DX is always going to equal the LX. Now, in reality, of course, some people will live beyond 101. They'll live to 102, 103. But the number of people alive at those ages is very small, that we don't have to extend the life table any longer. We might find that as more people live beyond the age 100, we're probably going to find more life tables are calculated past the age 100. But it makes the impact of the length of time that people live after the age of 100 makes very little impact on the overall life table. So we tend to finish the life table at 100 and assume and close the life table there. So those are the first columns of the life table: the age-specific death rate, the probability of dying, the probability of surviving, the number of people alive at exact age X, so the number of people alive at the beginning of each age group, the number of deaths between age X and X plus 1, so the number of deaths for each age group. We now move on to the final 3 columns of the life table, and these can get a little bit trickier to understand, so bear with me. I now need to look at the big LX column, and this is the number of person years lived between age X and X plus 1. Now, in an unabridged life table, this big LX is going to look very similar to LX. The big LX really gets important for an abridged life table, but I'm not showing you that example. So you will see that the number of person years lived between X and X plus 1 is very similar to the little LX. You'll see that it's just going to be a little bit smaller. So I'm actually going to start off by explaining what this figure here, 9,956 is. That's the number of persons years lived between age 1 and age 2. Now what that's saying, as you can see, it's slightly smaller than the number of people alive at age 1. The number of people alive at the beginning of the age group. The number of persons years lived looks at the number of years lived for those people who survive that age and those people who die during that age. So we know that 9,955.5 people survive that age group. Okay, so there were 9,957.8 people alive at age 1, and there were 9,955.5 people alive at age 2. So in total, that's the number of people who survive from age 1 to age 2. We also know that 2.3 people died during that age. Now, we have to make an important assumption about when people die. And what we assume in most age groups is that deaths are evenly distributed during the year. By that I mean that for people who die between age 1 and age 2, they're as likely to die aged 1 and 1 month as they are to die aged 1 and 11 months. So we'd assume that the deaths are evenly distributed. So that means that on average, for people who die during that first year, we assume that they live for half a year. So in total, there's only 2.3 deaths in this age group. There's only 2.3 deaths that occur between age 1 and age 2. And we assume that they're evenly distributed during the year, so that on average, the people who die during this age live for 1.15 years. So we assume that they live, that they contribute half a year each. That means that the total number of persons years lived between age 1 and age 2 is the number of people who survived plus half of the number of people who died during that year. We're assuming they contribute 6 months each. So that's how we calculate the big LX. The formula that I've actually used, which does exactly the same thing, is to assume that the total number of persons lived between ages 1 and 2 is calculated by adding together, if I look at that formula again there, 0.5 times L1 plus 0.5 times L2. So just going back to that formula here, that's another way of calculating the big LX. It's a way of looking at the number of persons years lived. So everyone who lives during that age group lives 1 year, and everyone who dies during that age group contributes half a year. Now, we do have to make an important assumption for the last age group, because we don't really know how many person years they're going to live, because we don't have anything to calculate in a subsequent age group. In order to calculate the big LX for the last age group, we make an assumption that the number of person years lived in that last age group is simply the number of people alive at the age group divided by the age-specific mortality rate. So if you look at the formula for the big LX for L100, we can see that that's calculated as E105 divided by B105. That's the number of people alive at 100 divided by the age-specific mortality rate for 100 and over. So that's how we get the value of 2.2.3. So that's the big LX. I just have to say a little bit about the big L0. It is not reasonable to assume in the first year of life that deaths are evenly distributed. Infants who die in the first year tend to die closer to birth than they do closer to their first birthday. So here we have to make an assumption that the infants that die during that first year do not contribute half a year of life. you will find different assumptions in different life tables about how much infants who die during the first year live. In this particular example, I've assumed that on average they live for 0.3 of a year. It used to be that in very low infant mortality societies such as the UK, we used to assume that as all infant deaths were associated with problems at birth, that the period of that first year lift was very small, and we used to assume that it was around about 10%. But in recent years, that assumption has been changed because due to improvements in medical care, we find that infants who do die during the first year can now expect to live a little while longer. So we tend to assume that infants who die during the first year now contribute 0.3 of a year. And if you do explore and you do end up working with life tables, you find that there's lots of different assumptions that can be used. But in this particular example, I've assumed that the 42.2 infants who die during the first year, that they contribute a third of a year. So that's the big LX column. And now we come to the TX column. And this is simply a sum of the LX column. It gives the total number of years lived from exact age X. So the first value here, T0, is the total number of years that someone will live from age 0. And it's simply the cumulative sum of all of these big LXs. So if I sum all of these LXs from 0 to 100, that's the value for the first TX. That's the value for T1, for T0. And the actual the actual formula that I have used for that, I've kind of started from the bottom. It's actually easier to think about calculating the TX starting from the bottom. So we go to the bottom of the life table, the T100, that's going to be the same as the big LX. So the number of persons years lived at age 100 is the same as the total number of persons years lived after 100. So that value is the same. If we then go to the T99, that's the total number of persons years lived from age 99. That's calculated by adding 127 and 202. That's the total number of persons lived during age 99 plus the total number of persons lived from 100 onwards. And we can calculate the total number of persons lived for each age working back up the life table. So that value of 524 for the total numbers of persons years lived from 98 is the total number of persons lived during the age 98 plus the total number of persons lived from 99 onwards. So we can think of the big TX as a cumulative summing up the life table. And then we come to the most important column, which is the reason that we often calculate life tables. It's the reason that it's the outcome that you'll be looking at for life tables. It's the life expectancy. And life expectancy is always denoted by the letter E. So E stands for life expectancy. E0 is life expectancy at birth. And simply, all we do to calculate the life expectancy is we take the total number of persons years lived at birth and divide it by the number of people alive at age 0. We divide it by the radix. So if we divide the T0s, which is 790,437, if we divide that by 10,000, we get 79.04, which is the life expectancy of birth for this life table using the assumptions that I have used to calculate the life table. And I have made a number of simplified assumptions. The ONS calculation of their life table is a little bit more complex, but I didn't want to be showing you too many assumptions. If we look at the next value, that's E1, that's life expectancy at age 1, and we calculate that by dividing the total number of years lived from age 1, 780,450, and we divide that by the number of people who survive to age 1. That's 9,957, and that's how we can calculate the life expectancies at all different ages. So I hope you were able to follow this particular video. There are resources about how to calculate life expectancies on the internet, and I will put some of those resources on the KLE.